Hey, good morning. Any questions? I'm slightly behind my schedule for posting the third assignment. I'm working on it. I just want to make up one more problem. So by 4 o'clock today, it should be up on mobile. But it is due 2 weeks from today. So right after your midterm exam. That week, that week. But I would encourage you to take a look at the problems, not the ones that you need to do by MATLAB, but the variations on that you can do by hand. You should probably take a look at it before the exam. And exam will cover everything that we see till the end of this lecture, okay, for the first midterm. I did record the tutorial session in my office afterwards and posted it on mobile also, because we did do something about Simulink and I wanted everybody to have an opportunity to listen to that. Because we were only 5 or 6 people yesterday. So take a look at it, and if that model works, then I might do these tutorials where I record these things from my office and post it, and then you can just do it at your own leisure, working with the computer and listening to it at the same time. I will be introducing a few other software as well that are used in the lab, as well as how it might be used in the industry, because you actually have a data acquisition from a plant, and then how do you put several forcing functions on the plant and take the response and analyze it for control system design. So we'll be seeing a variety of software. Except I'm not going to talk about HISYS. I guess you're learning that in other courses. HISYS also has some control tools that you can implement on that. The HISYS dynamic part of it. Okay, so in the last lecture, we basically looked at how to construct step responses to first order. We are still talking about first order transfer functions in MATLAB and in Simulink. And the current assignment, number 3, is going to be reinforcing these ideas. So I want you to, given a transfer function, a first order transfer function, and a first order transfer function with time delay, how do you generate the dynamic response in MATLAB using symbolic toolbox, where you actually get an analytical expression for the output and plot it out, and using built-in MATLAB functions like step and TF, and then do the same thing in Simulink. Okay? So that way you will be able to compare the strengths and weaknesses of each one of these methods. Today I want to start about the third type of responses that we briefly mentioned. First one was a step response, the other one was an impulse response, and the third one is a sinusoidal response. And we saw the reason why a sinusoidal response might be useful, because any arbitrary disturbance, you can capture it as a series of sine waves of different frequencies, because you can construct arbitrary functions through these Fourier series expansion, if you like. So later on, we will build on this and introduce something called the frequency response method, where we actually scan the entire frequency. But right now, we are putting in a specific known frequency omega as a forcing function, and we want to see how the system would respond. Is it going to be the same frequency or a different frequency? Is it going to be sinusoidal, whatever? Okay? So, what we remember, earlier what we had was y divided by x equals to g. G is some transfer function. Typically for us now, it is a first order transfer function of this form, 1 divided by tau s plus 1. But we can generalize that later on to other types of transfer functions. And x is the input that we are talking about, and y is the output. So the output is transformed by the transfer function by multiplying it by x. So I'm saying now x is going to be a sinusoidal one. How do we define that? We define that away from a steady state. So x, the input that you are forcing, is measured as a deviation variable from the steady state. So if you are looking at a graphical representation of this, this is x-axis and y-axis, okay, and this is your function x of t. Okay, and if this is the steady state, we are putting a sinusoidal around that steady state. So we are varying the process input in a sinusoidal fashion around that steady state at a certain amplitude A, which we decide how much, like in the unit step response, they said the step magnitude is 1. So in a unit impulse response, the magnitude is 1. But the magnitude could be anything that we want. So in this case, A is going to be the amplitude of that excitation, and omega is going to be the frequency, that is how fast are we changing the input. In that case, the capital X, the deviation variable, in the time domain will be simply x minus xs, because that is how we define the deviation variable. The actual variable minus the steady state value. So that simply becomes A times sine omega t. And A and omega are two parameters that we decide when we are enforcing a particular system. Now you take the Laplace transform of this forcing function capital X. Okay, take the Laplace transform of that, and what you're going to get is the forcing function in the Laplace domain. And this you just look it up in the table in an exam, or if you have MATLAB access, you just throw this at MATLAB A sine omega t. You ask it to take the Laplace transform of that. It will give you this A omega divided by S square plus omega square. Okay? That is the Laplace transform of the input. So the output then is going to be the transfer function multiplied by the input, and that is basically rewritten as simply dividing by tau. Okay, divided by tau every time, and I've written it as 1 over tau divided by S plus 1 over tau, multiplied by the forcing term A omega divided by S square plus omega square. So that is the solution, the output y in the Laplace domain. So we need to invert that to get back into the time domain. Okay? Any questions so far? Okay, so how are we going to do this in MATLAB? I've just given you the MATLAB command. First, define the symbols. There are a few extra symbols in this particular case, particularly the amplitude A and the frequency omega. I call it as W in MATLAB. And then I introduce something called capital T, which is 1 over tau. T is tau. And then time is lowercase t, and S is the Laplace variable, and X is the input variable. Okay? So this statement simply copies the particular function. Okay? You can see 1 over tau divided by S plus 1 over tau multiplied by A W divided by S square plus omega square. I pass this to my Laplace and I get the following output in the time domain. And I just want to analyze this solution. Okay? So y of t in the time domain will be given by a first part which contains e to the power minus t over tau. Okay? And then there are two parts that do not contain an exponential term. They contain only the sine and cosine of omega term. Okay? So what happens to this trajectory of the output as time evolves from 0 to infinity? The first term will drop out, decrease. Okay? So this we call as the transient part of the response. There is no steady state. Okay? That's what we learned from this, looking at this solution. In the step response, there is a new steady state. It goes from the old steady state to a new steady state. But when you have, in the impulse response, what happens? The original steady state is recovered. You're perturbing the system, the original steady state is recovered in impulse response. Step response, you go to a new steady state. In a sinusoidal forcing, there is no steady state because the response continuously oscillates with time. What is the frequency of the oscillation? It turns out that it is the same as the forcing frequency. For all linear systems, that is in fact true. Okay? So if the system is modeled by a linear set of equations, the input frequency will be the same as the output frequency, but there is a sine and cosine. There are two parts to it in the output. The input was a pure sine wave, the output contains both sine and cosine, which you can write as, using trigonometric identities, write it in this form. Okay? So sine omega t plus phi. So this is what we call a phase shift. By using trigonometric identity, sine a plus b equals sine a cos b plus cos a sine b. Right? Using that identities, you can get the equivalence between these two parts. They are the same, but what I have done is I have dropped this term out because I'm looking at what we call not a steady state but an equilibrium response. The response is also changing with time as long as the input is changing with time, but it has the same frequency, its amplitude is different. Okay? The output amplitude is the input amplitude divided by square root of tau square omega square plus 1. Okay? So the amplitude could be diminished. Okay? And then there is a phase shift by phi. And phi is given by tan inverse of minus omega tau. In both the amplitude ratios, we will call this as the amplitude ratio and the phase shift. So what it says is when you put a sinusoidal input, the output is the same sinusoid with a frequency, with a phase shift and with an amplitude that is changed. If you plot this, am I going fast or are you guys okay with that? Any questions? Okay. Okay. So this is how the output will look like. Okay. So here I call the initial part as the transient period. Sorry. The transient period, which I have not plotted. Okay, that is the period where it will still be changing periodically, but there will be an exponential decay. Okay, and once the exponential part decays, then the rules will further change in the amplitude. If you look at the amplitude, it is the same. Okay, so that is the input amplitude, and this is the output amplitude. This is still the thermometer problem. Now you might ask, how am I going to force a sinusoidal change on a thermometer? Can you think of an example where I have a thermometer, right? Remember, this model we have started with by dipping a thermometer into a vessel and developing a transfer function format, first order transfer function. Right. So all you need to do is expand your time horizon, and you can see a lot of situations in nature where the oscillation is periodic. So if you look at a house and you're just monitoring the room temperature where the thermostat is set to turn it on and off at night and day, for example, and record the temperature over a period of 3 or 4 days, you'll find some sort of a periodic variation. The same thing occurs in nature. If you put a thermometer outside but just watch over a year, you'll find some sort of a repetitive behavior. Okay? So it is possible, and those kind of, in fact, in Canada, I guess it is important to take into account the variation in the temperature in designing how deep should you bury the pipeline so that the water doesn't freeze. Okay, so I give as a problem in the heat transfer course, where you have to look at the transient heat convection from the surface of the earth into the ground, okay, where the surface temperature is changed periodically. And you need to know below what temperature will the temperature not go below 32 degrees, okay, so that you bury the pipe that deep. So there are a lot of situations where you'll find this kind of periodic oscillations, or you can force the periodic oscillation in a particular plant to extract some information. The information that you will get are the amplitude attenuation, the amplitude ratio between the input and the output. Okay, that is this number, and the phase shift. What do we mean by the phase shift? It is basically the same sine wave. The output is basically the same sine wave with the same frequency, but the point, the time at which it reaches peak, is not the same as the time at which the input reaches peak. Okay? So if you take the peak to peak time difference, that is your phase lag. Okay? So the output is lagging behind the input by a certain time interval. Okay? And that's what the phase lag means. Okay, 0.056 minutes in this particular example. Any questions? We're talking about a lot of concepts. You might have seen it before, forgotten, I don't know. If it is new, if there are questions, you have to please ask me. Yeah. This is taking a total input and then output. You're putting a sinusoidal input on the system, and you're monitoring the output, and you're watching and plotting the output. So this is the output curve. This is a first order response. The transfer function is a first order transfer function. Yeah. Good question. Why is there an amplitude decrease? It depends on the capacitance of the system. Okay, so in a sense, it depends on the time constant. Okay, the amplitude ratio depends on both the time constant of the process and the exciting frequency that you're enforcing. Okay, so in the degenerate case where the frequency is 0, I guess, then you'll get the same output as the input, right? But physically, if you want to understand that, it simply says that if I have a heated tank and I'm changing the inlet temperature of the tank in a sinusoidal fashion, the tank has a large heat capacity. So the fluctuations in the outlet are going to be much smaller than the forcing that you're doing on the system, because it has a capacity to store the heat and release the heat. Yeah. From 517 to here. That is a trigonometric identity that you need to use. What you need to do is you need to recall that sine A plus B is equal to, I don't remember this, sine A, I think it's something like this. I will write it down, plus cos A sine B. There's a formula, a trigonometric identity, okay? And so you just need to treat this as A and B, two numbers, and then do the expansion, and you can show that it is equivalent to the previous one. And nowadays, I must admit that algebraically I'm not very sharp, because I rely on some math and symbolic toolbox. So you just throw this at it and say simplify. It will simplify it for you. Okay. And I'm not going to test you on those knowledge either, because there are more important things that you need to learn in this course. Okay. Okay. Any other questions? Okay, I have given you the MATLAB code. I would encourage you to try it on your own. Okay, I don't want to take up the time demonstrating the same thing. What I want to do is now develop a few other physical examples that also give rise to first-order transfer functions. Okay, so we just use the thermometer problem as an example, but we have looked at two other examples in the past. So let's just revisit them very quickly and derive the transfer function. This is something that I expect you to be able to do in the first midterm exam. Okay? So if I give you a problem, analyze the problem, do the Laplace transform, derive the transfer function for the physical problem. It could be a reactor, it could be a separation unit, a heat exchanger, whatever. Okay? So let's revisit this particular problem where we have a tank, a heated tank with a heater. This is the very first problem that we started the course with. And we have inlet and outlet flow rate are the same. So there could be variations on this. So in this particular example, the level doesn't change because inlet and outlet flow rate are exactly the same. Okay? And the inlet temperature is something that I can change. I put a step change or impulse change or whatever. And I'm monitoring and controlling the outlet temperature, which is the same as the temperature in the third tank. It's said very well. Okay? So we developed the mass balance, the energy balance equation, energy balance. And we had this equation. And then we looked at possible solutions in the time domain, but I want to derive a transfer function now, okay, so that I can use the power of Simulink and other tools to look at controller design for that problem. Okay? So this is the rate of accumulation on the left-hand side equals rate in minus rate out for the energy. Okay, WCTI is the energy coming in, WCT is the energy leaving, and the steady-state version of it. Remember, I'm reinforcing this idea of getting this in terms of the deviation variable. Okay, for linear systems. Later on, we will see how to do that for nonlinear systems. Okay, so under steady state, this is going to be equal to 0, and I get this equation: WC times TIS minus TF. So the subscript S indicates that these are the steady state variables. Then I subtract one from the other. Okay, when I subtract one from the other, I get this TI minus TIS, and then T minus TS from these two terms on the right hand side. On the left-hand side, what I've done is, this is 0, but I can write this as DTS divided by dt, because Ts is a steady state, it's a constant, so its derivative is going to be 0. Okay? So I use that fact to write this and introduce the deviation variable. So now I call x as a deviation in the forcing function, which is the inlet temperature Ti minus Tis, the deviation from Ti. Okay? And T minus Ts is the output y, which is my output variable. Okay? So the differential equation then, in terms of the deviation variable introduced here, this simply becomes capital Y. Okay? And this becomes capital X, the input, and this whole factor, rho v c divided by Wc, becomes tau. That is the process time constant. Okay, so this is really nothing new in here. We're just doing the same operations that we learned for the heat exchange problem, the heated tank problem. Okay, so this is once again a first order ordinary differential equation. Now, y is the dependent variable, the output, the unknown, and x is the forcing function. Time is the independent variable, and tau is the time constant for this particular case. Okay, so take the Laplace transform of this, and you will get, for the derivative, you're going to get s times y of s. Tau remains as it is. On the right hand side, this is x of s, and this is y of s. Now combine this y of s, and you get, lo and behold, exactly the same type of transfer function. So physically different problem with a different physical time constant. Okay? So the time constant is something, in order to get the time constant, you need to know something about the process. You need to know what is the volume of the vessel, what is the heat capacity of the liquid, things like that you need to know. Okay? But mathematically, they are exactly the same. They are governed by the same equation, so you can now ask questions like, what is this? How does this system respond when I put a step function, impulse function, sinusoidal function, etc. Once you understand the dynamics, then you can say, okay, now I want to control it. What kind of controller will work well for this particular transfer function? Okay. Any questions on that? Yeah.
Could you explain again how you went from dt and dt to dt minus ds?
Okay. It's really very clear there, right? So you're asking about this one? Okay. So just take the derivative of this. Keep in mind that Ts is a steady state value. Steady state value meaning it is not changing with time. Ts is constant like this. Okay. So do the expansion d dt of t minus Ts, because it's a linear operator, it's going to be dt over dt minus dts over dt. But Ts is a constant, so its derivative is going to be 0. Okay? So by adding that, I'm not really changing the equation. Right? Why do I add that? I add that because I want to reframe this as my deviation variable. That's the only reason. Okay? Any other questions? If you feel comfortable, as I said, you should be able to do this. The first order for the second order system, 2 first order systems, all these variations. And in your current third assignment, there will be one problem on the side where you have to derive the transfer function for a reactor, for example. Okay. So are all the steps clear? Write down the dynamical equation, take the limit of a steady state by setting dt equal to 0, and subtract one from the other, introduce the deviation variable, take the Laplace transform, and express it as a ratio of output to input. That is your transfer function. Okay. Now, one more example. This is also an example that we have seen. This is not the previous example is actually practically realizable. This example is not practically realizable, and I would like you to kind of question why it is. But what I'm telling you is, you have a tank, and you have flow rate that is changing with time now. In the previous case, the flow rate, mass flow rate was constant. Now the flow rate is changing with time. And the outlet flow rate is changing in this particular fashion. Q0, Q out, is H divided by R. R is the resistance that you apply by the valve. So depending on the valve opening. So if the valve is wide open, R could be very small. The resistance to flow is very small. So they have more flow. Okay. As you close the valve, the resistance is larger, you cut down the flow. So we are saying that Q0 is H over R. Okay. And this height then can change. As I change the inlet flow rate, the outlet is not going to change immediately, so there will be an accumulation. And if the level goes up, I'm going to have more outflow from that. The outflow is affected by that level, the level is affected by the inflow and outflow, the difference between them. Is the physical description clear? Any questions on that? Okay. So we are defining Q0 as H over R. The units, of course, are meter cube per second. And so R should have the appropriate units because H has the units of meter. So R should have the units of second over meter squared, because that equation should be dimensionally consistent. So R is a number that represents the design of the valve, and it will have the units of second over meter squared. So once again, applying this accumulation equals input minus output. Now it is on the mass. Okay. So A times H. A is the cross-sectional area of the tank. A times H is the volume multiplied by rho, the mass. ddt, the rate of change of mass, equals mass in minus mass out. Now the rho is a constant, it's a liquid, so you can cancel that out. And the area of the tank is constant, so you can take that out, okay, and you get the following equation. Now, in future, let me just point out that you could have a tank like this, and it is draining. What would you change in here? A is not a constant anymore. It's not a cylindrical tank. Okay? And the other case could be you have a tank, cylindrical tank, but in horizontal orientation. It's commonly used in chemical industry. Right? You'll find in the refinery cylindrical tanks are vertical or sometimes they're horizontal. What happens here? If I have an inlet and if I have an outlet, once again the area is changing. Okay? So you should be able to do a geometrical calculation to relate how the area changes with the height. Yeah.
If you had a triangle, that's what the values of
No. It's still the order depends on the order of the derivative. Okay, so it will still be governed by a first order transfer function, but we would call that as, I think I introduced the terminology earlier, linear time invariant versus linear time varying. I think you asked the question for clarification, right? So if any of the coefficients here are changing with time, then you have a linear time varying system. Okay? It's still a linear system, and it's still a first order system. When you get a second order system would be when I take this and feed it into that. So I have two tanks in series. One is a conical tank, and the height there drives the flow out, and that goes into a cylindrical tank. Now we have two first order systems that are connected. So the response of the height in the cylindrical tank is governed by what happens in the height in the conical tank. Okay? So that would be a second order system. Any other questions? Okay, so now we are going to do the same process. We derive the equation and take the steady state limit, set dSdt equal to 0, put the subscript s, so that gives you the steady state equation, the steady state flow rate related to the steady state height. Okay? Then subtract one from the other and introduce the capital Q as a deviation variable for the input and capital H as the deviation variable for the output, which is the height. Okay? And when you do that, subtract one from the other. For the same reason, I can write this as dH minus HS, because HS is a constant, and you get the following equation in terms of the deviation variable. Okay? And now combine all the terms that are the unknowns, H on the left-hand side, take the Laplace transform, and you get exactly the same type of equation. So the transfer function is still a first order transfer function. A constant divided by another constant times s plus 1. Okay? That is always a first order transfer function. Now, why would this model be not realistic? Here I'm asking you to remember something that you learned from fluid mechanics course. If you use this model to control the height of a draining tank, this model won't work well because it's not a good model. Do you remember from your fluid mechanics course? This course I won't examine you on, that I will give you, but this is, I constructed this so that I get a linear equation. But in reality what happens is this Q0 is a constant times square root of H. Okay? That comes from Bernoulli equation. Okay? So when a tank is draining freely, driven by the height, the flow rate is proportional to the square root of the height, not the height itself. And that would make it a nonlinear problem. Okay? So then we need to worry about linearizing it so that we can develop a linearized model and a transfer function from that. Okay? So this is a realistic situation. This is kind of an idealistic one. Any questions? Okay, let's do an example. Okay, so in this example, what I have is I have a tank into which I am pumping fluid at a steady rate of 10 foot cube per minute inlet flow. Okay, and I give you the resistance coefficient for the valve, which is 1 over 9 foot per cubic foot per minute, and the time constant is 1 minute for that process. Okay. Watch this carefully. What I'm saying is at time t equal to 0, the flow is increased to 100 foot cube per minute for exactly 0.1 minutes. Okay, and then I shut it off. So it's as if I'm dumping a certain amount of liquid into the tank over a short period of time. What am I trying to achieve? What model, what input forcing function am I trying to approximate? Is it step? Is it impulse? Is it sinusoidal? Because this is all the description you will have in a problem. You need to decide what is the appropriate. It is an impulse, okay, but it is not an exact impulse. An exact impulse will occur instantly. You're dumping all the water at an instant. So this problem also teaches you how to calculate the so-called energy content or the magnitude of the impulse. Okay. Now I'm claiming that the magnitude of the impulse is 9 foot cube. How did I arrive at that number? 9 foot cube over 0.1 minute. So what I'm doing is, from 10 foot cube, I've increased the flow rate to 90 foot cube, or 100 foot cube. So I have increased it by 90 foot cube per minute. Okay, but I'm applying it only for 0.1 minutes. So if you multiply that, you get for over 0.1 minutes how much of water you are actually dumping. Okay, and that comes out to be 9 foot cube. Okay, so that is the area under this curve. In this idealized impulse, the area under the curve, which would be the total amount of water that you have added. Okay, so this is going from 10 foot cube per minute to 100 foot cube per minute over 0.1 minutes. Okay, so what is the area under the curve? And that is going to be 9 foot cube. That is going to give you the total amount of water that you have added. Is that clear? Okay. Now plot the response. Plot the height versus time for two cases. One is the idealized impulse. The other case is actually treated as the step response. So you can look at the description as an idealized impulse where this d goes to 0, the 0.1 goes to 0, is as if you are adding all 9 foot cube in an instance of time. Then what would be the height? And for that the solution is given. Okay, so this is the transfer function model between the input and the output, and the input is an impulse, and for impulse it's simply 9. R is 1 over 9, which is given to you. Tau is 1. So it is 1 over 9 divided by s plus 1 multiplied by the transfer function q for the impulse, which in this case the magnitude of the impulse is 9, so it gives you 9. So that gives you the output as 1 over s plus 1. Take the inverse Laplace transform, and in the time domain the output is going to look like this. Just a pure decay, going back to its original steady state. Impulse always perturbs it, and it will recover to the original steady state. Okay? But the real situation is more like this. QT, the real QT is one where at time t equal to 0, by this green line, you are increasing it from 10 to 100. That is, you are increasing it from 0 to 90, if you like. Okay? You are increasing it by 90, plus 90. And then, at t equal to 0.1, shown by the red line, it's an opposite step response, where you bring it down by minus 90. So you can look at Q of t as the sum of two step responses. Are you following me? This is, I think, one of the things that we learned how to do in the MATLAB session yesterday. Okay, so you can superpose several of inputs to produce more complicated inputs. So in this case, the real signal is something like this. It goes from 10 to 100, or equivalent 0 to 90, and comes back over an interval of 0 to 0.1. So if that is the input, how am I going to construct the output for that? Okay? Is that clear? Any questions on that? Okay. This one we will do in MATLAB. First one I'm showing you is if Q of t is given by this expression. Q of t is 90 multiplied by ut. What is ut? Unit step function. Okay, unit step function. U of t goes from 0 to 1. Of course, in this case, multiplied by 90. And what is U of t minus 0.1? Do you understand that symbol? It simply says that at 0.1, there is a step change. And it is a negative step change. It goes in the negative direction by the same magnitude 90. Okay? So the graphical representation that I have shown here is mathematically represented by this equation. In MATLAB, how would you represent that? Do you know? If you have to write this function in MATLAB, Q of t, what is the command? I think I might have mentioned it once. It's called Heaviside function. A Heaviside function is a step function. So the name, the syntax is Heaviside. And we will see that soon. MATLAB will display that. Okay, so the Laplace transform of this step function, the first step function is very simple. Okay, it is 1 over s. So it's going to be 90 over s. It is the second one that you need to worry about. Let me ask you, what would be the difference between the first step function and the second step function? Laplace transform of that. Laplace transform of a step function is always 1 over s, right? But the step has to occur at 0. Okay? If the step occurs like this, and this is 0, then the Laplace transform of that is 1 over s. We've seen that. What is happening in the second one? It is a step function, but it is a delayed step function. It is delayed by 0.1. Okay? So here you need to recall what we call the translation theorem that we saw in Laplace transform. Again, I'm asking you to review that also in your current, because I've not given you an example, you won't remember it until I put it. So you have to do it in an assignment. So this assignment has an example of how to use the initial value theorem, the final value theorem, and the translation theorem in the Laplace transform. Okay. So the second one is delayed by 0.1, and its Laplace transform, you can always throw this at MATLAB, and MATLAB will give you. Its Laplace transform is given by that delay, e to the power minus 0.1 s multiplied by 1 over s. Okay? So this e to the power minus 0.1 s comes because of the delay. Okay? And the theorem that we are using is basically this one. Okay? F of t minus a. This is valid for any function, not just a unit step function. If you have Laplace transform of a function that is delayed by a, then it is the Laplace transform of the original function multiplied by e to the power as. In this case, a happens to be 0.1. Okay? So it is the Laplace transform of unit step function, which is 1 over s. So the 1 over s appears in both. I've taken that as a common factor out. Okay? Multiplied by the. So the thing that you need to worry about is where is this coming from? It is coming from the delay in the process, the shift in the process, and using the shift theorem in the Laplace transform. So the solution in the Laplace domain then is 10 times 1 over s times s plus 1 minus the delayed function divided by s times s plus 1. So I need to define this function and then take its inverse Laplace. Okay, so let's maybe do this here. MATLAB puts the output as a heavy side. Okay, that's what I meant by the delay. So let's go to MATLAB and try to implement this. Okay. So use XST. And G, maybe let me see if I can just copy it. No, I guess I cannot. I need to type it. So I'm going to define the transfer function G as equal to 10 times 1 over s. If I make any mistake in typing, please correct me. Okay, 1 over s divided by s plus 1 minus exponential of minus 0.1 times s, which is the delay, divided by s divided by s plus 1. Okay, and then I say y as equal to I Laplace of g. So this is how it outputs. The output has a step function in it. Okay, so it is heaviside t minus 0.1 multiplied by e to the power 0.1 minus t minus 1. So it's a fairly complicated looking expression. So you can say, well, throw it at easy plot and see whether it plots at easy plot y. And let me do it in the range of 0 to 10. Somehow the axis is not showing the whole of it. You guys remember what I need to do to show the whole thing? View, yeah. Figure palette. Thank you. It's I really made a mess of it now. I'm not sure why it is doing this. It always controls the y-axis. Property editor. I'm sorry, I'm going to waste time. It's supposed to go up to, I guess, 0.9 and then come down. But you're not seeing the graph. It's basically taking off and then coming back. And it is implementing this 0.1 delay. Which is going to go to the full value over 0.1 and then start declining. Whereas the pure impulse response will be starting at 0, it will decay. So there will be an error in the real system compared to the pure impulse response over the time interval of 0.1 or 0.2. But later on, you will see both of them agreeing with each other. Now, instead of struggling with this, I will just show you the result because I have the graph here. Okay. So this is how the true impulse response will be in the red graph, and the blue one is the step change that is occurring over 0.1. If I put this up and down step change, then the response is given by the blue one. So that will be the real one. And they agree reasonably well far away, particularly after time equal to 1. Okay, so to make it agree more and more, what do you need to do? you need to cut down this interval over which you dump this. If you, instead of dumping it over 0.1, if you dump it over 0.01, the agreement will be even better. Okay? Okay, any questions? So it gives you an idea of how to interpret impulse response input, okay, the area under the curve. That's basically what I wanted to illustrate with that particular problem. That's probably a place where we will draw a line for your first midterm exam. Okay? The next concept is a fairly simple concept that I wanted to illustrate with a simple example. This is the idea of linearization. Why do we need linearization? Simply because most of the chemical processes are nonlinear. Okay? So nonlinear systems are difficult to handle. You can handle it numerically, you can look at the response, but control system design is typically done using linear models. Now, can we do that? The answer to that is it works well as long as the plant is operating under steady state, because you can find out what the steady state is and develop a linear model around the steady state, and the model will be a good representation of the dynamics around the steady state. But if you are departing from the steady state for some reason, then the model itself will fail. So this is why in industry they will often retune the control parameters, recalibrate to find out if the plant has shifted to a new steady state. Now these concepts I'm going to illustrate using a very simple example. Okay? The example of linearization is done with this particular polynomial. I have a third degree function, okay? And when I set this equal to 0, I'm going to find the values of x that satisfy that particular function, and it's a third degree polynomial, so there are 3 roots. And these would be similar to the steady state solutions for a differential equation, for example. Okay? So I have solution that satisfies these functions, and I want to construct an approximation of the function around these solutions. Okay? Graphically, what do I mean by that? Let me go down and I'll show you the figure. Here is the figure of that particular function. Okay? The red line is the third degree polynomial, and you can see that there are 3 values where the function will be 0, and one of them happens to be here. Okay? Another one somewhere here. That's where the x-axis will cross. So if I draw an x-axis, the places where it crosses are the 3 solutions where the function is 0. What I want to do is, for the third solution, I want to construct an approximate representation of the function. Okay? I'm going to replace that nonlinear curve by a straight line, a linear equation. Okay? That is where it's given by the blue. Now, if I at this stage give you this problem, how many of you can construct that straight line for me? What do you need to do? Draw a tangent to that curve. Draw a tangent to the curve and say that tangent is an approximation to the function, and you can use that tangent to calculate what the value of the function is in the neighborhood of that function. So if I blow this up, the function looks like this, and the tangent looks like this. So the tangent is a good representation. The error between these two, the vertical distance is the error. It's small. As long as I am close enough to that steady state, that solution. But if I want to calculate the function value at some value of x that is here, the function is here, but the tangent is predicting the function to be here. That's a poor representation. Okay? So this idea is what I want you to get at. You can apply the same idea to a differential equation by taking a tangent, by taking the derivative, and constructing the function. And I've shown you how to do this in MATLAB with a piece of code. Okay? So originally, I have a function which is actually defined. I started out by saying that this function is x minus 3, x minus 2. Expand it. Okay? Because I'm placing the solutions at 3, 0, and 2. So I've started with a factored version of the equation, and the expand function symbolically in MATLAB will define that function f for me. Okay? So you can do this in MATLAB, for example, expand x minus 3 times x times x minus 2. So that's the expansion and gives you what the polynomial is. So that's how I define the function. Then I say solve that function. So there is a command called solve, which takes the function and finds those three values of that function. Okay. So solve, in this case, what do I type? I need to type answer because I didn't store it in any variable. So these are the three rows. I started off with these three rows. I should know that. Okay. So solve just confirms that. And then this diff. Now I'm in trouble because I don't have that function saved. Okay, let me save it as f. Good question. Can you take a guess? The same thing, but what is the form of input that root expects? Root expects 1 minus 5, 6. X and 0. I'm glad you asked the question because it points out that root expects only numerical values of the coefficients of the polynomial. Okay, so it has to be 1 is the. Now, how does root determine the degree of the polynomial? By the number of coefficients that you have. So if you didn't put the 0, for example, you will simply take it as a quadratic and it will give you 2 rows. By putting a 0 in the last place, I'm saying this doesn't have a constant term. It's still a cubic polynomial. So it should give you the same answer. Okay? So the difference is roots takes polynomial coefficients, solve takes an expression, a symbolic expression. So solve is more powerful in the sense you can throw any function at it and it will try to solve for that function. It's not restricted only to polynomials.
It looks like it's doing analytics as well.
It is. It is, yeah.
Compared to roots just doing compare.
Right, yeah. That's the main difference, yeah. Okay. I guess we are kind of out of time. What I would recommend, I guess, is that you go through these steps, which is basically to generate the two graphs that I've given. And when we restart, I will go through this linearization again. So very important concept, we need to learn how to apply to differential equations so that we can develop linearized transfer functions for nonlinear dynamical systems. Okay? All right, let's stop there. So look for your assignment by 4 o'clock today.